All right, this is a fantastic question that I've found in the collaboration space. So let's have a look at this one. We've got a rational function, but it's not in the nice form that we like. What is the nice form that we like these ones to be in? It's really nice if we have it in something along these lines. F of x equals a over x plus h plus k. Because then we can clearly see, well, here's what I've multiplied by. That's my vertical stretch or dilation. Adding a number, that's my my vertical translation up and down, and the h is the horizontal translation left and right. So it'd be really easy to draw from that. We don't have this in the right form at the moment. So what we're going to do is we're going to start with that left-hand side, ax plus b over cx plus d, and we're going to create something that's going to cancel the cx plus d, so I can end up with a nice constant plus some other number over x plus h. Now, I should point out I chose a there, but it's not obviously corresponding to this one. That's just the form we want to get it in. So it's not part of our solution. Let's work with this expression here. Now, I've already said the first thing I want to do is I want to get some sort of multiple of cx plus d so I can cancel with that denominator. Well, that's lovely, chewers, that you want to do that, but what would I have to factor out so that this ax becomes cx? Well, obviously, when I multiply it, I've got to undo the effect of multiplying by c, which would be to divide by c. And I should have an a in front of my x. So if I actually put a over c in front of that bracket, then when I expand that first term, I'm going to have a over c multiplied by cx. Oh, and of course, the c's will cancel, and it's still just equal to ax, isn't it? So that's okay. I've got ax there. I'm supposed to have b, and instead I've got this a over c times d. I've cheated a little bit. What do I do about that? Well, the way I find it easiest, let's just leave the b that we had there. And this is a little bit like when we add something on to complete the square and we have to subtract it again. What I've added on this time is a over c multiplied by d. So ad over c. If I've added that term, what do I have to do? Subtract it. That's right. So I need to subtract AD over C. Now, if we just expand that, I'm going to do it over here on the side in a different color. Just to convince you that what I've done has actually worked. Let's see if that should return us to the same expression. Let's see if we got it right. So I'm going to go A over C times CX. So the C's will cancel, and I'll just have AX. So far, so good. A over C times D, well, that's AD over C. I've still got my B there, that's okay. And now I've got this negative AD over C. Well, okay, positive AD over C, negative AD over C cancel. This is still all over the denominator CX plus D. Yeah, they're equivalent expressions, aren't they? So what was the point of changing it into this form if it's just worth the same thing anyway? Well, just like completing the square, it makes life a little bit easier. Let's separate this fraction into two parts. I'm going to have the first part of the numerator there and the second part of the numerator there. And I'm going to write these two fractions separately. Remember, when we're adding, if the denominators are the same, we can write them as separate fractions. So here's cx plus d is my denominator. And the first bit is a over c multiplied by cx plus d. All right, well, that's so far so good, not too bad. Plus, my other fraction is b minus ad over c, all divided by cx plus d. And what was the whole point of doing this? Well, now, the cx plus d's in this first fraction are going to cancel, and I'm just left with a over c, plus my other expression, b minus ad over c, all divided by cx plus d. And you'll notice that is the expression we wanted over here. How has that helped us? Well, now k, remember in this form, k is what? It is a vertical translation. So the vertical translation, usually for these rational functions, it's the x-axis, that's the asymptote. So what is the horizontal asymptote now? Well, it's shifted to y equals a over c. How do I know it's that? Because this expression here, b minus ad over c, all those B's, A's, D's and C's are numbers, aren't they? So that's just a constant, like we've got in that form there, a constant. That's just a number divided by some sort of expression in x. Now that fraction can never equal 0, because remember the only way it can equal 0 is if that whole expression up the top equals 0, which in this case we'll have to assume it doesn't, and we should make a note of that. But then that's why the whole expression can never equal a over c, because this part on the right will never equal 0. So that's why your horizontal asymptote is always a over c. So a rule of thumb, you can always just use a divided by c to find the horizontal asymptote. I prefer to actually rearrange each of them, and I'm even going to go further. Let's make one up and just show you what I mean. So let's say we've got f of x equals 3x minus 2 over 2x plus 5. So I want to rearrange that so I've got it into the form where I can see the translation. A bit like completing the square, but not quite the same. Let's go ahead and do it. So I want this to be 2x plus 5. I already know I want that in my numerator. There's my 2x plus 5 in the denominator. Okay, it's supposed to equal 3x. So for this 2x to equal 3x, I'd need to multiply by 3 and divide by 2. Okay, this negative 2, I've just left it alone there, haven't done anything to it. But I have, by putting this plus 5 there, created a new term. That's plus 15 over 2, isn't it? 3 5s are 15, so I've added 15 over 2, or 7.5. So I need to subtract 15 over 2. What's the beauty of doing that? Well, the first half, I can now write 3 over 2, 2x plus 5 over 2x plus 5. And of course, there's brackets around that 2x plus 5, otherwise I've just changed what it's worth, and I wouldn't do that. Here I've got negative 2, so that's negative 4 over 2, minus another 15, it's negative 19 over 2, so it's negative 19 on 2, divided by 2x plus 5. What do I do now? Oh, that's right, they cancel over this side. So I'm running out of room, I don't want to have to scroll anywhere, I want you to be able to see the whole lot. So let's just say the 2x plus 5 is cancelling that first fraction, so now I've got 3 over 2 minus, and this is 19 over 2 divided by that, so you can, just to make it a little bit easier, 19 over 2 outside of 2x plus 5. So you can see we've had a vertical dilation, a reflection, a horizontal compression, and we've had a shift of 3 over 2. And if you go ahead and plot that in Desmos or something, we should see that the horizontal asymptote is at 3 over 2. Why don't we do that now and see if I'm not telling a lie or if I'm telling the truth. So here I am, I'm in Desmos. Now our equation was 3 over 2 minus 19 divided by 2 outside of 2x plus 5. I think that's what it was. Let's just double check and see if I got that right. 3 over 2 minus 19 over 2, 2x plus 5. That looks right. Now I claimed that the asymptote would be at y equals 3 over 2. Well, let's put in y equals 3 over 2. And look at that. If we zoom out, there's our asymptote. So you can always use a rule of thumb. If you just take the coefficients of the x terms, if I've got a function in that form, the horizontal asymptote is a over c. The vertical asymptote is just where the denominator equals 0, negative d over c. I don't remember those things. I like to rearrange it so that I can understand exactly why a over c is the horizontal asymptote and why negative d over c is the vertical asymptote. It's really important that you understand where they came from. But in the end, if all you want to do is memorize it, you're welcome to do that. I hope that helps the explanation. If it doesn't, just come and chat to me in class and I'll go through it again. But maybe watching this once or twice should help you out. Really good questions I've got tonight. It makes me really happy. Keep up the great work, guys. Bye.